Okay, good morning, everyone. How did your homework go as usual? If you have any questions, put them on the chat before we start. Okay, any questions besides 13? All right. Okay, so we're gonna start do those and then we're gonna do some problems together. Okay. So every time we do a problem, we think about the strategy to solve those related rate problems. So we do number 11. Sorry, let me fix this up a little bit. Okay. All right. Number 11, expanding squares. The size of a square increases in length at rate of 2 meters per second. At what rate is the area of the square changing when the sides are 10 meters long? All right. So we have a square. We have a square. And let us imagine that, we're heating the square in a way. So this is my square. Okay, and with time, the square is actually expanding. Okay, so the square is expanding. The side is getting larger, both sides, so it's expanding, just like the circle we had yesterday. So the side is expanding. The side is getting larger with time. Okay, so that's really the idea. So this is S, which is that's called S, the side. Okay, and as S increases, the side increases, the area of the square increases as well. That's really the situation we have. Now, the side increase at a rate of 2 meters per second. So this one increase 2 meters per second. So, and as the side increase, the area is going to increase. And the question is, how fast is the area increasing? All right. So the first part of doing this problem, we identify what's varying in this problem. So what is changing in this problem? And now I want you guys to answer me. So we introduce the variable. We draw the picture, we introduce the variable. And here everything changed with time. So when they are saying that the side is expanding, it means there is a time variable and we're talking about, and this side changes with time. So what are the variable in the problem? The side is changing, the area is changing. So we're going to introduce our variable. Let S of t represent the length of the square at time t. Those are the main variable. And the other one is the area. So those are the two things that are changing. Area, A of t, we're going to call it A because A stands for area, is the area of the square at time t. Okay. Now, what do we have? What's given to us? And what's the unknown in this problem? What is given to us? And what is the unknown? Okay. Now what's given to us? They are telling me that the side is increasing. And it's increasing at a rate of 2 meters per second. So this side, every second, it increases by 2 meters. Every second, it increases by 2 meters. It means the derivative of S with respect to time is 2 meters per second. So that's a unit of the derivative. Now, what do they want me to find? As the side increases, the area is increasing. And they want me to find how fast the area increases with respect to time. Okay, and they want me to do that for when S is 10, and then that's part A, and then when S is 20, that's size B. Okay. So this increase, the area increase, how fast is it increasing? And this is like yesterday, the area does not increase by the same amount, doesn't increase by the same rate. S increases at the same rate, but the area, as we realize, is increasing at a faster rate. It's increasing more and more with time. All right. So this is my first step. That's my second step. Now, what should I find right now? What is the third step in the process? We need to find an equation between the variables. We need to find an equation that relate the variable. So we read the problem, we ask ourselves what's changing, what they are giving us, and then the main thing we need to find what is the relationship. So here, side is changing with time, and the area is changing with the side. So we have those two variables. What's the relationship between them? Okay, what's the area in terms of S? The area for every moment in time, no matter what t is, well, no matter what t is, the area is always s squared. No matter what the time is, doesn't matter what time is, the area is always s squared. So that's the relationship between the area and the side. Okay, now I know how fast this is changing. I want to find how fast this is changing. So now I'm going to rewrite this by including a of t. And my idea here is that I want to emphasize that the underlying variable is t. If we lose track of that, we actually kind of lose track of what's going. So for every time t, at t equal to 1, let us say, whatever s is, a is s squared. At t equal to 2, whatever s is, a is s squared. So for every time, the area is s times t squared. So that's the equation that relates the variable, so which is very simple in those problems. Now we differentiate with respect to time both sides. And find an equation between the rate. So that's really now we have to find a relation between the rate. All right, we say that no matter what time is, a of t is equal to that. So the derivative with respect to t of the area is the derivative with respect to t of s of t squared. Now, derivative with respect to t of the area, which is really what I don't. This is dA dt equal. What's the derivative of that? S is a function of t. So now we're going to use the chain rule. Okay, so that's the outside here. So that's the inside in my problem. That's the inside. And the outside is the squaring operation. So the derivative is 2 times the inside, which is s. I'm just not going to write s of t for make it a little bit simpler, times the derivative of the inside. Okay? That's the relation between the rate. So now if I know the s dt, I should be able to find the a dt and vice versa. If I know this, I should be able to find that. So now the last step in the process, we use the given to find the unknown. So now use given to find unknown. That's usually the last step. Given, use given to find the unknown. Okay. So now what's given? I put them here on the side to remind us. What we have is that this is equal to 2. And my unknown, I need to find how fast the area is changing for 2 time into when s is 10 and when s is 20. This is really what we have to do. All right. So now I just plug in those values into the equation. All right. So let us see. That's what I want. And I have the SCT. I have S. So we just plug everything back in here. So now the first problem, I will do it when S equal to 10. What's the ADT? Okay, so basically I am plugging into this equation right there. That's really what I am doing. It's 2 times S times the SDT, which is gonna give me 40. And now what's the unit? What's the unit? It's how fast the area change with time. The unit of area is, because S is measured meter, unit of area is meter square per second. It means once the side is 10 meter, so once the side is 10 meter, then after 1 second of that, the area increased. The area increased by 40 meters square. So when the side is 10 meter, that's how fast the area is increasing. Now when the side is 20 meter, the area is increasing at a faster rate. It's 2 times 20 times 2. It's going to give me 80 meters square per second. So when the side is very big, at 20, if we change the time a little bit, like by 1 second, then the area will increase by 80 meters square. Okay, so that's really the approach we're going to use for every one of those problems. And now I will do, of course, number 13 and 15, and then we're going to do something which is a little bit harder, but it's the same spirit. But now I need your help. So every time I'm going to do something, I'm going to ask, what am I supposed to do at this stage? What is the pattern that you're going to be following? Okay. So let me look at one of them. So let's see number 13. Okay, that's number 13. Expanding isosceles triangle. So it's the same ideas here. Basically, they are not the legs of an isosceles right triangle increase in length at a rate of 2 meters. So understand the picture. The legs of an isosceles triangle increase. So we're thinking about a triangle, isosceles. It means the legs are equal. That's my isosceles. It's a right. Sorry. It's a right triangle. So that's my triangle. Those are equal. And the legs are increasing. So the legs here are increasing at a constant rate. So as times really go by, this is increase and this is increasing. So let us say this side increase like that, and this is going to increase by the same amount. So now I have a whole new triangle. That's my triangle. Everything is increasing. A little bit later, this side increase, my triangle, this side is going to increase. So I have my whole new triangle. So that's really the picture. Things are increasing with time. Okay. And it's an isosceles. And they are telling me that this side, those legs, are increasing at a rate of 2 meters per second. So as this side increase, again, what's happening is that the area increases. The area increases, the area increases. And the question is how fast the area increases. Okay? So I will draw now one picture now. So let us see at time t, that's the situation. And this is the situation at time t. This is my triangle at time t, and this is my picture. So we're going to give those a name. Okay. So what's my first step? I want to stop talking. You guys will help me out. What's the first step in solving those problems? Please go on. We have hard problems to work on today, so I want help. What is the first thing I do when I solve those problems? Get going. Before finding equation, which is coming very soon. Before finding equations, what do? I introduce the variable. I have to know what is changing in this problem. So what is changing in this problem? So I have to introduce variable. What's changing? Get back to you. If you don't walk them very carefully, you won't be able to do those problems. The area and the side. That's right. So what's changing is the side or the leg and the area. So we have to start by giving those names. I'm going to call the leg. We can call it anything we want. So let me call the leg S, for example. So that's the leg. And since they are equal, so this is the same side and the area. So step number one, what are my variables? So we're going to call S of t, because changing with time, is the length of the leg, length of leg at time t. Those are things which changing. And A of t, the area of the triangle at time t. That's the first step on the process. So these are my variables. Those are the things which changing with time. Step number 2 is what? What then should I do before I put the equation? What now I should do? Back to you. What's given, what's the unknown? Exactly, that's how we have to understand what is given to us and what's the unknown. What's given is how fast the leg is changing with time. So what's given is the SDT, which is, they give us the same number as before, 2 meters per second. The unit makes sense. S is measured in meter, T is measured in time. And what is the unknown quantity in here? It's, they want me to find how fast the area is changing. So that's what they want me to find. And we know that the areas change at different rates. So they want me to find how fast the area changing when the leg are 2 meters. So when S is 2. I don't know why they're giving me the same numbers all the time, but whatever. Okay, so now that's the given. Now I know what I want, and that's part A of the problem. Part B is different. Now I find the equation. What's relate the area of the triangle and the side? So now we find the equation. So the equation between the variable. Okay. Now what's the area of a triangle? What's the area? Back to you. What's the area of it in general? What's the area of a triangle? What's the area of a triangle? Half the base times the height. But in this case, that's an isosceles triangle. The base is S, the height is S. So since it's a right triangle, the base is S and the height is S. So it's a half S squared. That's the equation between the variable, okay? So this means that for every time t, no matter what time is, the area, so the S is changing with time, but whatever S is at this time, the area is half of S squared. So that's the relation between my variable. Now, once I find the equation, what do I do? Back to you. Because you should be able to, if you answer your questions, then it becomes an easier process. What should I do right now? So I found the relation. S changing with time, the area, which changes with S, will change with time as well. What should I do at this stage? Back to you. Differentiate with respect to time. So now we're going to differentiate with respect to time. Okay. So now I say, all right, the derivative of the area. So this is the piece that I am differentiating. So here I have a function of time. Here I have function of time. I don't know what they are exactly, but I'm not really have to concerned about them. I don't need to know them. It's equal to the derivative of this expression with respect to time. So let's write this down. If I have S of t. Okay. So dA dt equal. A half is a constant. I can pull it out. All right. What's the derivative of S of t squared? Now we've done this several times. S is my inside. So it's the derivative of the outside times the derivative of the inside. So finally, what's dA dt? 2 and 2 cancel each other. It's S times the S dt. So that's the equation with that relate the rate. That's why I call the related rate. The word related rate because the rates of the surface of the sides and the rate of the area are related. That's really where the word related rates is really. So if I know how fast one is changing, I know how fast the other one is changing, and vice versa. If I know how fast the area is changing, I should be able to find how fast the site is changing. The last piece of the problems is usually use the given to find the unknown. So now that we found the relationship, so the last piece is like finding the derivative. Once you find the derivative, then you plug in at the given value. And that's really what I'm doing right now. So now finally I have to find, so I use the given. Now part A is the problem, part A of the problem. The given is the SDT equal to, and I have to find the ADT when S is equal to 2. Okay, so I just plug in. So we'll see what I have. I have the ADT equal S, the SDT. It means the ADT equal S. I know what S is, 2 times. The SDT is 2. It's equal to 4. Okay, and now what is the unit? Back to you. I want a unit. I've talked so much about it. I want the unit. So for what?
Meters square per second.
Unit of area per unit of time. Okay. So let's look at part B. And B. B, they want me to find the ADT. So, and the given is the same. Find the ADT when what? When the hypotenuse is 1 meter. Okay, so that's B. So they want me to find the ADT when the hypotenuse is 1 meter. Now, the relation I have is the ADT equal, so that's the relation between the rate, is S, the length of the side, the SDT. Okay, the SDT is always 2, so that hasn't changed. But now they want me to find the ADT when the hypotenuse is 1. So how can I find it? How can I find the ADT? I know the S, that's it too. The ADT is what I know, what I need to find. It's equal to. I don't know S, but can I find S? If the hypotenuse is 1, can I find S? Yes or no? Yes. How can I find S? Let us remember Pythagorean theorem. So I don't have S in this problem they want me to find. What does Pythagorean theorem tells me? S squared plus S squared equal to 1. So at a certain time, the hypotenuse is 1. So how fast is the area changing? It means 2S squared equal to 1. It means S squared equal a half. S is the square root of 1/2. So my S is the square root of 1/2. Okay, so they, instead of giving me the side directly, okay, they make you think a little bit. They give you the hypotenuse, but it's not a big deal because if I know the hypotenuse at a given time, I can figure out the side. So the ADT is, now this could be written square root of 1/2 is 1 over root 2 because I can break up my root 2. So it's 2 over root 2 centimeters square per second. Now part C. So those are basically the basic problems. Those are the basic problems. So let's look at part C. Okay, I will read it. What it is. At what rate is the length of the hypotenuse changing? So now the problem is different. The problem is at what rate, so it's not area anymore. They don't want the area. At what rate is the hypotenuse changing? And they don't want me to find at any specific value for S. It means they basically want me to find a formula for how fast is the hypotenuse changing. Okay. So the picture is the same now. Let me go back to my original picture. But what are we looking at now? This is my picture. This is S, which is changing, and that's the hypotenuse. So the hypotenuse was this piece right now. As S gets larger, the hypotenuse getting larger. That's the hypotenuse. As S gets larger with time, that's the hypotenuse is getting larger. So the hypotenuse is changing with time. And their question is, how fast, if they want basically a formula in this problem, how fast is the hypotenuse changing? It means, was it changing 2 meters per second? Was the hypotenuse changing 3 meters per second? How fast was this hypotenuse changing? Okay, that's really my question. So it's not a question of area, it's the question of the hypotenuse in this problem. But the process is the same. So now I have different variable in a way. So now I have, this is my at time t, this is my picture at time t. This is S. I want to know how fast the hypotenuse is changing. So now my variables, I need another variable which represent the hypotenuse. So now what are my variables? Okay. S of t, which is the length of the side, no change in that. That's S. And then the hypotenuse, I'm gonna call it H because H stands for hypotenuse. So H of t is length of the hypotenuse. Okay, so now I'm changing because they want me to find how fast the hypotenuse is changing, not the area. The given is always the same in this problem. So tell me how fast the side is changing. The unknown is how fast the hypotenuse is changing with time. Okay, so that's the process. So that's the given, that's the unknown. Now I need to find an equation that relate the hypotenuse at the side. So now we go after the equation. Okay, what's the equation? Back to you. Who give me the equation that relate hypotenuse at side? Look at the picture. So the way we're gonna find the equation is either we know the formula or we use the geometry of the problem. So what's the equation that relate hypotenuse and the side? Okay, I'm having good answers. I have to go after Pythagorean theorem. So that's this time I don't have a formula. I know I have a formula, but I need to use the geometry. The geometry tells me that h squared is s squared plus s squared. Absolutely correct. It means h squared is 2 times s squared. So that's the relationship between them. So this is gonna give me that h squared is 2 s squared. Okay. Now there are 2 ways of doing this problem. I'm going to do it in one way, and another problem I'll do it differently. So I can basically solve for h here because it's simple. And I will get h equal what? Because it's very easy. What's h here in terms of s? Give me h in terms of s. So that's h squared. It's 2s squared because the s's are equal, and that's important in this problem. It's the square root of 2s squared. Right? But square root of 2s squared is not smart to keep it like this. It's basically s times the square root of 2. Okay, so that's the equation that relate my variable. That's really what I want to go after. Very good. Now, finally, we differentiate everything with respect to time. Differentiate with respect to time. Okay. Now, I suppressed h of t. But we have to keep it in mind. Even if I don't write h of t, what in my mind really is not this. So in my mind, always is that height at every time t, that's the way I think, is whatever the side is at time t times the square root of 2. So in my mind, always, this is h of t, and this is s of t. There's always this underlying variable, which is time. Now I differentiate with respect to time, and I get the following. The derivative of the hypotenuse with respect to time, that's really what I want, is equal to. Now square root of 2 is a constant, I don't have to worry, times how fast the side changes with time. So if I know how fast the side, I know how fast the height. So dh dt equal. Now I know that this is given to me 2. That's what's the given, is 2 times the square root of 2. Okay. What's the unit of the h dt? What's the unit? Back to you now. Meter, because that's a hypotenuse. Unit of hypotenuse is not square anymore. That's meter per second. Another actually interesting is the hypotenuse changing at a constant rate in this problem? Is it a constant rate? I mean, they didn't tell me find the hypotenuse at this for this value of s, because look what's happening. No matter what time is, the hypotenuse is changing at the rate of 2 times square root of 2, which is 2 times 1.4, which gives me like 2.8 meter per second. And it's a constant rate because there is no s in here. There is nothing. It's just, regardless what s is, this number is constant. It means the height is changing, the hypotenuse is changing at a constant rate with time. So every second, s changed by 2, the height changed by that much. Every second, that's what's going on. Okay. All right. Any question before we go on? So now number 13, I'll just give you, I did number 13 because we want to start, we're going to do one more problem today, which is a little bit harder. 15, okay, I'll look at 15 and I want to spend time to solve one problem, which is slightly different than those. And okay, so I look at number 15. Okay, number 15 is the following: expanding circle. But here they tell me that the area increases at a rate of 1 centimeter square per second. So basically, it's like yesterday problem. We have, imagine we have a circle expanding with time, expanding with time, expanding with time. Okay, and so the area is increasing. As the area is increasing at a constant rate. It means every second the area increases by 1 centimeter square. So the area increases. As the area increases, the radius is going to increase. And their question is, if I know how fast the area increase, do we know how fast the radius increase? Okay, so the question is, find the rate at which the radius increase when the radius is 2 centimeters. So I will just do part A in this problem. All right. Again, we go through the process. So the question is, how fast is the radius increasing? So we know how fast the area, how fast is the radius? All right. So my two variables here are the radius and the area. So A of t is area at time t. R of t is the radius at time t. Okay. Now, what is given to us? They tell me how fast the area changed this time, not the radius. What's the unknown? They want me to find how fast the radius change. Sorry. When the radius is 2. So, and this is equal to how much? 1 centimeter square per second. All right. Now I got the number. So they want me the area changing at this rate. They want me to know how fast the radius change when r is 2. So again, the same process. What's the equation that relate the variable? So what's the equation? That's a circle for every time t. So for every time t, I'm talking about a circle. So that's my circle at time t. So I fix my time. And this is the radius. And the area is this. So the relationship is that the area is pi times the radius square. Okay, so just like we did yesterday, but the only thing different is that they gave me how fast the area. I want to find how fast the radius, which is not should be a big problem for us. So this means that at every moment in time, whatever the area is, that's the relationship between the area and the radius. Now we differentiate. Okay, so we get the derivative of the area with respect to time equal pi times. This is my inside. So u square is the outside. So it's 2 times the derivative of the inside. So that's the relation between the rates. So if you write it a little bit nicer, that's 2 pi times r times the r dt. That's the relation between the rates. So if I know one, I know the other. Now finally, we use the given to find the unknown. So use given to find unknown. Right. So what's given to us? What's given is the ADT. That's what's given to us. What do we need to find? The RDT. So I write this down here. Given the ADT, it's 1. Find the RDT when R equal to 2. Okay, that's what we have to find. So now we just have to plug in everything into here. So I know the ADT. I know R. I need the RDT. That's how this problem is working. So the ADT is 1 equal to pi. R, they give it to me, so they make my life easy, times my unknown, which is the RDT. And now that's what I have to find to solve for. So now I solve for the RDT, 1 over 4 pi. And the unit is the unit, always unit. If the area is centimeter square per second, it means the radius is measured in centimeter. So R is measured in centimeter, time is measured in second. Okay, so that's the rate at which my radius is changing. All right. Okay, so today as a B, you guys should be able to do it. It's not hard anymore. Instead of giving you the radius, they're giving you the circumference. It means they're giving you 2 pi r equal to 2, and then you find the value of r. Okay. All right, today at least we'd like to do one problem, all of us, and let me see what the problem is. We're going to understand it and do it. So let me see if I can get all the problem down up here clearly. Yeah, that's it, I think. Okay. So that's another related rate, one of the classical one. We're going to look at it, read it, and work with it. All right. I read it, and you guys, if you have a sheet of paper next to you, it will be very helpful. So you can kind of interact with the problem. So here we have a ladder. It's 10 feet long, and it rests against a vertical wall. So start slowly to build a picture in your head what's going on. So we have a ladder. It's 10 feet long. It rests against a vertical wall. Now, somebody is pushing, so the bottom of the ladder slides away from the wall at the rate of 1 feet per second. So imagine somebody holding the bottom of the ladder and moving it at a rate of 1 feet per second. So every second, the person is moving the bottom of the ladder by 1 feet. Now, as the bottom of the ladder being slided away, the top of it is going to fall down. And the question is, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? Okay, so I read the problem again, and now we're going to draw pictures to understand what's going on here. So we have this ladder, which is 10 feet long. So I draw a little bit one here. We have a ladder. It's 10 feet long, and it rests against a vertical wall. So that's my wall here. In a minute, I draw definitely a bigger picture. Okay, so that's my ladder. And somebody took the bottom of the ladder and start sliding it away at a certain rate of 1 feet per second. As the bottom is moving, the top is going down. Bottom is moving, the top is going down. So if the bottom is moving at 1 feet per second, how fast is the top of the ladder going down? By how much per second? So that's really when the ladder is 6 feet from the wall. We take care of that later on. Right, so what are the variables here in this problem? What's changing in this problem? So let's draw now a bigger picture. Since we've read that, let's draw a bigger picture right here. And then we're going to introduce what's changing. So this is my wall. This is my wall. It's fixed. And I have the ladder, which is standing against the wall. And the ladder is 10 feet. So this is a fixed number of 10 feet. And what's really going? So at the beginning, let us say the wall, if you want, at the beginning, maybe the ladder was just straight like this. That's at t equal to 0. Okay, that's at the beginning. Then somebody took the bottom here and moved it away. So after 1 second, that's where my ladder is. So it was up to here because the ladder is straight, vertical, and then it went down because somebody moved the bottom. Then somebody kept moving the bottom. So after another second, let us say the bottom is here. So it was here, now it is here. So this why the top actually went down. That's really my picture. Somebody kept moving this, and this one went down. And the question is, how fast is it going down? So I have this tip of the ladder. It was here. Then it moved down. It moved down. So imagine you have an object which is actually changing. So the object was here, then it's here, then it's here, then it's here. So it's changing it's changing. How fast is it changing? 1 feet per second or more. So what are the variables? What are the things that are changing in this problem? Anybody can tell me anything. Anything comes to your mind. It's helpful. The height and the base. So she's telling me the height and the base. Now let us make sense. What do we mean by the height? What do we mean by the base? So what are the variables? What's changing is the base. It means how far is the bottom of the ladder from the wall. This is changing with time. That's really changing. What else is changing? How high is the top of the ladder? These are the two things that are changing. Okay, so my variables are. Okay, now I would like to take another piece of paper because I want to fix time in my head and do it. So at time t, that's my problem, that's my wall, and that's my ladder. That's the ladder. So this is the situation at time t. Okay, that's what's happening at time t. And everything is changing. Everything is changing. So at time t, so we're going to call the variable. We're going to call x of t from here to here. That's my x. So it's the distance from the bottom of the ladder to the wall. To the wall. Those are what is changing for me. And I'm going to call y of t distance from top of the ladder from here. So that's my y of t. That's my y. Top of the ladder to the ground, if you want, to the floor. So those are the things which are changing. I have to introduce my variable. X of t is changing. From here to here, that's changing. And this is changing. Y is changing. Both those are changing. This is. Now, what is given and what's the unknown? What's given to us? They're telling me that whoever is sliding this ladder is sliding to bottom at the rate of 1 feet per second. What does this mean to you? It means x is changing by 1 feet per second. Every second, x changed by 1 feet. Every second, x changed by 1 feet. So this piece here, as he's sliding it, is changing by 1 feet per second. It means the x dt is 1 feet per second. Now, unknown is how fast is, I want to know how fast y is changing, because as x change, y is changing. I want to know how fast y is changing with time. It means what I am after is how fast y is changing with time. And they want me to do that when x is 6 feet away from the bottom. Okay. All right. So this is what's given to us, and this is what we need to find. Now, the question is, what's the equation that relates? So now I am after the equation that relate the variable. Okay, so what's the equation that relate the variable? So once we understand the problem, we read it like several times, then we start finding the equation. The equation is usually either given to us like a formula, volume in terms of whatever sides, or we have to look for it. What's the relation between the variable? We use the picture to find. Okay, anybody can give me what's the relationship between x and y? It's not hard. It's not hard. Look at the picture. We don't have really formulas here, so we have to look at the picture very, very carefully. Okay, somebody is telling me that if you look at the picture, Pythagorean theorem tells me that for every moment in time, x squared plus y squared equal to 10. 10 squared. Thank you very much. All right, so Pythagorean theorem tells me that. So now I'm going to say, okay, what's the equation between the variable? So the equation is for every moment in time, x squared plus y squared equal to 100. So 100 is my 10 squared. Okay, so that's the relation. That's what connects the variable. Very good. Now I need to find the relation between the rate. So, but I want to keep in mind here, I actually like always to remind you that this is really x of t. So this is really a function of t. And this is always y of t. Because if you lose track of that, we actually are in bad shape. Okay. Now we're going to differentiate with respect to time. Okay. All right. And this time, I'm going to differentiate in a different not in a different way, but I don't want to solve for x in terms of y. I know that I know the x dt and I want to find the y dt. I don't really want to solve for one in terms of the other. So be very careful. I'm not going to do that. The way we're going to think about it is like we did implicit differentiation, quote unquote. I'm going to say that this is equal to 100. It means that the derivative, watch careful the way I'm going to do it because it's easier sometimes. The derivative with respect to time. So this is a function of time of x squared, actually x of t squared, so you understand it's time, plus y of t squared is equal to, so I'm differentiating this with respect to time, is equal to derivative with respect to time of 100. So instead of solving for one in terms of the other, I will say, okay, the derivative of that is equal to the derivative of this. So let us compute the derivative of each one of them. Sorry. My apology for that. It wasn't supposed to happen. Okay, so the derivative of this is equal to that. So what does this mean? X of t here is my inside and y of t is my inside. So what's the derivative of x of t squared? We do it very carefully. It's 2 times x times dx dt plus, what's the derivative of y? It's 2y dy dt equal derivative of 100 is 0. Okay, so in this problem, instead of solving for y in function of x, which you can do it, I'm not saying you cannot. So, but we're going to learn another way of doing it. I said the derivative of this is equal to the derivative of that. Now, what's the derivative of x of t squared plus y of t squared? I'm using the sum rule. So I found the derivative of the first plus the derivative of the second. Now, what's the derivative of the first? It's 2 times x, so this is the inside, 2 times x times the x dt plus 2y dy dt. Okay, and this will give me basically the relationship between the rate. So that's the equation that relate the rate basically. So I can divide by 2 across the board and I get x dx dt plus y dy dt equal to 0. So that's the relationship between the rate. Now at this stage, if I know the x dt, I can find dy dt. If I know dy dt, I can find the x dt. I know I can do anything I want at this stage. So now the final part is use given to find the unknown. All right, so what is the given here? What's the given to us is, I write it here, given, and a nice piece of paper is in order. Okay, so this is my relationship. Now what's the given? What is given to us, because you don't have the problem in front of you, is that the x dt equal 1 feet per second. And what they want us to find is dy dt when x is 6 feet. That's the problem. Okay, so now I go back here and I need to substitute verbatim. So I rewrite the relationship that I have between my rate, and then I say, okay, what I have, what I need to find. Okay, and I'm gonna substitute. The x dt is 1, no problem, ask. X is 6, plus dy dt is my unknown, that's the one I don't want to, equal to 0. But now, what is y? This is really the question. I don't know why. I don't know why. But what do I know? I want y when x is 6. So if I go back to my picture now, ask myself, if x is 6, at a particular moment in time, the ladder will be 6 feet away from the wall. At this particular time, how far will be y down the wall? So if this is 10, what's going to be my y? So this formula requires us to know y at the specific moment in time when x is 6. So how can I find y? So at this stage, I use my Pythagorean, x squared plus y squared equal 100. My x is 36 equal 100. It means my y squared is 100 minus 36, which is going to be equal to 64. It means my y is equal to 8. So at the moment, exact moment, where x is 6, y is 8. And now I solve for my y. And this would give me dy dt equal minus 6 over 8. It means dy dt equal minus, and this is 3, 4, and the unit. Okay, what's the unit in this problem? What's the unit? Y is measured in feet because x is measured in feet times in second. And now one question before we go, why it is negative? Why dy dt is negative? Why dy dt is negative? Why this derivative is negative? What is y doing with time?
Is it because it's sliding down the pole?
Exactly, because it's going down. Because it's going down. So if I want to graph y with respect to time, when I graph it, how is the slope of the tangent line? Because I'm finding dy dt, the slope of the tangent line. How is this going to be? Is it going to be increasing or is it going to be decreasing? As time go by, y was 10 because the ladder was straight. But as time go by, y is actually decreasing, 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 decreasing. So the slope will have to be a negative number. Okay, so exactly the y dt, we should expect a negative number because y is decreasing with time. Okay, and that's the end of that. All right, so tomorrow you guys will have a quiz as usual, and you will have more problem along those lines. There are still 2 types of problem I would like to do with you that deal with related trade, and we'll do that tomorrow. Okay, good luck. Bye.